Hello, I'm Mr. Clee and this is my second video for C5 quantitative analysis. First part of the video is on percentage masses from formula and the second part is on empirical formula. The aim of the first section of the video is to give you an understanding of how to calculate the percentage by mass of an element within a compound from its formula. So for example, if you were given the formula H2O, what percentage of that by mass would be hydrogen, which in this case is 11.1%. So here's the example of ammonium nitrate. Ammonium nitrate has the formula NH4NO3. If you want to work out the mass of nitrogen within this, you need to use the atomic masses of all the atoms and all the elements involved. The first step would be to calculate the atomic mass of the entire compound. Nitrogen, 14, 4 hydrogens, another nitrogen, and 3 oxygens, give you a total of 80. The second stage is to isolate the nitrogen within that. Now there are two places where nitrogen appears in this formula. There are 2 nitrogen atoms in total. So 2 times 14 gives you 28. By dividing the mass of nitrogen by the mass of the relative molecular mass of ammonium nitrate, 80, and times your answer by 100 because it's a percentage, that tells us that 35% of the ammonium nitrate is nitrogen by mass. Wherever you see the pause sign in this video, it means it might be a good opportunity to pause the video and have a go at the questions yourself before I go through them. First question, working out the percentage by mass of sodium in sodium hydroxide. Mass of sodium is 23, oxygen 16 and hydrogen 1, giving you a total mass of 40. If you divide the mass of sodium, 23, by the total mass, 40, and times it by 100, it gives you 57.7% sodium by mass in sodium hydroxide. In this example, working out the mass of oxygen in copper sulfate, the first step is to do the mass of copper sulfate as a whole. 63.5, add 32, add 4 times 16, which is 64, giving you a total of 159.5. If you divide the mass of oxygen by that number and times your answer by 100, that gives you the percentage mass of oxygen within the compound, which in this case is 40.1% oxygen within copper sulfate. You can also do this experimentally if you did a reduction here of copper oxide to copper and then try to find out what percentage of the original copper oxide was copper. What you'd have to do is you'd have to have the mass of the copper oxide to start with, which you can calculate by doing 34.9 minus 31.9, giving you 3 grams, and then the mass of the copper left over at the end of the experiment, which is 34.3 minus 31.9, giving you 2.4. Using the same equation that you did before, 2.4 over 3 times 100 to give you the percentage mass of copper in copper oxide would give you 80% copper in copper oxide experimentally. The second part of this video is how you calculate empirical formula. Empirical formula is slightly different from molecular formula. It is essentially the simplest version of a formula. So where you can have something along the lines of for ethene, you can have C2H4. The simplest version of that formula, i.e. the ratio of carbon to hydrogen, is CH2. That's the empirical formula, the simplest version of the formula. It's usually the first thing that's calculated when a new compound is discovered. Here's another example. Below, just about, is the displayed formula for butane, which is C4H10. The simplest version of this is C2H5. This is the empirical formula, the closest whole number that you can get the simplest version of the formula. Here's some simple examples for you to try. The first one, CH3. Second one is also CH3. You get CH2O for glucose, PbO2 for lead oxide, and then probably the most complicated of the five. The reason for this is because you've got carbons and oxygens in different places. So the first thing to do is add up the number of carbons, the number of hydrogens and the number of oxygens, C2H4O2, and then simplify that as CH2O. So the first empirical formulas were calculated from experimental data, and this is the way that you need to be able to try and work out the empirical formula of a compound. For example, magnesium oxide forming from the oxidation of magnesium. So this is the set of results, some example results from an experiment where magnesium is oxidized in a crucible to form magnesium oxide. The mass of magnesium before the experiment was 0.72 grams. The mass of magnesium oxide was 1.2 grams. So the difference between the mass of magnesium oxide and the mass of magnesium gives you the mass of the oxygen involved in this reaction. The other piece of information that you require is the atomic masses of the two or more elements involved in the reaction. So this is the sequence you have to go through each time when trying to calculate the empirical formula of a compound. The first thing to do is to write the mass of each of the compound of each of the atoms involved into the table. So magnesium we had 0.72 grams and oxygen we had 0.48 grams. The next thing you need to write down is the atomic mass of both of these. Magnesium is 24 and oxygen is 16. What you need to do then is to find the number of moles. If you remember, to work out the number of moles, you do the mass of the compound that you have divided by the molecular mass, or in this case the atomic mass. In both instances you get 0.03 moles of magnesium and 0.03 moles of oxygen. In this case, because both of the numbers are the same, you divide by 0.03, but if one of them was smaller you'd divide by the smallest number. So 0.03 over 0.03 gives you 1, and the same applies there. This gives you the ratio of magnesium to oxygen. It's in a 1-to-1 ratio, therefore the formula is 1 mg to 1O, or MgO. I'm going to try another example here, trying to work out the empirical formula of a compound that contains sulfur and oxygen when they are 50% sulfur and 50% mass. When working out empirical formula using percentage data, you just assume that it's that many grams. So if you've got 50-50 in this case, you just assume it's 50 grams of sulfur, 50 grams of oxygen. If it was 25 and 75%, you'd say 25% and 25 grams and 75 grams. It doesn't matter whether you're dealing with data in grams or data as a percentage when working out empirical formula. There's an opportunity to try this one before I go through the answer. Sulfur and oxygen in a 50-50 split, so it's a percentage. 50% sulfur, 50% oxygen. The next stage is you need the atomic mass of each one. Sulfur has an atomic mass of 32 and oxygen 16. Using the same equation to work out the number of moles by doing the mass divided by the atomic mass, we find that the number of moles of sulfur is 1.5625 and the number of moles of oxygen is 3.125. Each of these numbers is divided by the smallest of these numbers. So the smallest one is 1.5625. That number divided by itself gives 1, and 3.125 divided by 1.5625 gives you 2. That tells you the ratio of sulfur to oxygen is 1 to 2, meaning the empirical formula is SO2. Incidentally, this doesn't necessarily mean that we're dealing with sulfur dioxide, although in this case it's the most likely compound. The final example I'm going to show you today is a compound that contains hydrogen, carbon and oxygen. A 2.3 gram sample contains 1.2 grams of carbon, 0.3 hydrogen and 0.8 oxygen. Another good opportunity to have a go on your own before looking at the solution to this. Right, firstly, the mass in grams of each of the constituent parts. Carbon 1.2, hydrogen 0.3 and oxygen 0.8. Then you need the atomic masses of the atoms involved. Carbon is 12, hydrogen is 1, oxygen 16. Again, using the equation to work out number of moles, which is mass divided by, in this case, atomic mass. 1.2 divided by 12 gives you 0.1. 0.3 divided by 1 gives you 0.3, and 0.8 divided by 16 gives you 0.05. Next step is to identify the smallest of these numbers. So you do 0.1 divided by 0.05, which gives you 2. 0.3 divided by 0.05 gives you 6, and 0.05 divided by 0.05 gives you 1. Checking back for whole numbers, we can give a simple empirical formula of C2H6O. That concludes this video on working out percentage composition and empirical formula. If you need any further assistance on either of these things, please see me, I'm Mr. Clee, or any of your science teachers.